A population growth with harvesting problem models how a species population changes over time when it's subjected to harvesting, such as fishing. Suppose a fish population grows at a rate proportional to its size with proportionality constant 0.04 per year. Initially, there's a population of 10,000 fish, and fish are harvested at a constant rate of 200 fish per year. What we're going to do is we're going to set up and solve the differential equation for the fish population, capital P of T. Once we have the solution, we can use that to describe the long-term behavior of the fish population. Let's first set up our differential equation. Our differential equation starts with the change in population with respect to time, and we're going to write that as d capital P dt. And the change in population is going to be equal to the growth rate minus the harvesting rate. We are told that the population grows at a rate proportional to its size. So the way we write that mathematically is we have a proportionality constant K, and then we have a P. That just means that the rate dp dt is proportional to P. And then we subtract off the harvesting rate, which we're told is 200 fish per year. So we just subtract off 200. Now we can go ahead and substitute in what K is. We are told that we have a proportionality constant 0.04 per year. So we can write this as d capital P dt is 0.04p minus 200. And we can also add on our initial condition. We are told that the initial fish population is 10,000. So we can say that P at 0 is equal to 10,000. And there's our differential equation and the initial condition. Now what we need to do is solve this differential equation. This differential equation can actually be solved two ways. This is a linear ordinary differential equation, and it's also a separable ordinary differential equation. I am going to solve it as a separable differential equation. Before we go ahead and separate the variables, I want to multiply by 100 just to get rid of that decimal. So let's say that this is 100 dp dt is equal to 4p minus 20,000. Now let's separate the variables. On the left, we have 100 dp, and we're going to divide this by 4p minus 20,000. And on the right, we get dt. Now we can go ahead and integrate both sides. We have 100, and because of the 4 here, our derivative needs to be 4 dp. So we are going to have to divide by 4. And that gives us natural log absolute value 4p minus 20,000. And on the right-hand side, we have a t, and then we add on our arbitrary constant plus c. Let's go ahead and solve for c. Let's use our initial condition that p at time 0 is 10,000. So this on the left, we have 25. Natural log absolute value 4 times 10,000 gives us 40,000 minus 20,000 is equal to t, which is 0, plus c. So this tells us that c is equal to 25 natural log of 20,000. We'll drop the absolute value because it's positive. Now we can rewrite our solution as 25 natural log absolute value 4p minus 20,000 is equal to t plus c, which is now 25 natural log 20,000. Let's now combine our natural logs. So I'm going to pull the one on the right over to the left. And we just have a t on the right. On the left, we have 25 natural log 4p minus 20,000, all divided by 20,000, is equal to t. Let's go ahead and divide by 25. And then we can exponentiate each side, and that gives us 4p minus 20,000, all divided by 20,000, is equal to e to the t over 25. Let's now solve for p. So we have 4p is equal to 20,000 e to the t over 25 plus 20,000. And then all we have to do is divide by 4, and we get p is equal to 5,000. Hang with me, we are almost done. And we can combine this, pull out the 5,000, and then we have 1 plus e to the t over 25. And let's put in units, we are working with fish. And there's the solution to our differential equation. Notice that because this term right here is positive, our fish population is going to grow exponentially. And that's exactly what we have to answer for our second question. We want to describe the long-term behavior of the fish population. We can write that as the limit as t goes to infinity of p of t is equal to 5,000 times 1 plus e to the infinity, and that is equal to infinity. So we can say that our population grows exponentially. Before we're done with this problem, I want to show you one more interesting thing that relates to the population growth. Let's go back up here and look at this part of our equation. We are going to have what's called an equilibrium solution, meaning the population is not going to grow or decline, and that's going to happen when this right-hand side is equal to 0. If we solve this for p, we get that p is equal to 5,000. This tells us that if our initial population is greater than 5,000, we're going to have exponential growth. And if it's less than 5,000, we're going to have exponential decay. And our population will become extinct.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.